Video lesson 4 tonight has to deal with isotopes and shorthand notation. You may be asking yourself, what does the nuclear power plant from The Simpsons have to do with a smoke detector that you might find in your household? Both of these make use of isotopes, and we're going to talk more about that tonight. What I would like you to be able to do after completing this lesson in practice tomorrow is to identify the number of each subatomic particle for an element, provided it's shorthand notation. You'll also need to be able to identify an isotope and explain the difference between isotopes for a given element. Now in class today we practiced how to determine the number of subatomic particles given the periodic table information or a drawing of that atom. What shorthand notation is it uses the same information that you might find from the periodic table. So if we use helium, for example, here, and this is what you would see on the periodic table, so something you would be comfortable with here. From this, we can find our atomic number, which is my number of protons. So I have 2 protons. If I know my number of protons, I also know my number of electrons, which is 2. The last part of this here is finding my neutrons. So if I take the rounded atomic mass and subtract my number of protons, I'll get my number of neutrons. The reason this works here is that the atomic mass is equal to the number of protons and neutrons, since those are the only 2 subatomic particles that have mass. For shorthand notation, we're going to use helium as an example here again, but instead of our atomic mass being on bottom, we now have our atomic mass up top in the upper left-hand corner. Our number of protons and electrons, or the atomic number, will be in the lower left-hand corner now. One way to know that you're dealing with shorthand notation is that if the upper left-hand corner number is bigger than any of the other numbers provided, that's going to be your atomic mass. Atomic mass is always going to be larger than atomic number. But still using the same information, we see that we have 2 protons, 2 electrons, and 2 neutrons. Let's do one more example here together. If we look at sodium, which is atomic number 11, we can see that we have 11 protons. Using that same information, we'll have 11 electrons. Then once I do my calculation, I'll find that I have 12 neutrons. The next part of our lesson is going to focus on isotopes. I'm going to begin our discussion on isotopes of why do we really care about isotopes. And so isotopes are extremely beneficial for us in medical fields, research, agriculture and food production, commercial products, and the generation of power. So for commercial use, 2 examples that we have are smoke detectors, which use Americium-241 to help detect if there's a fire in your house. And previously, with glow-in-the-dark watches, you would use radon, which is a radioactive isotope. In the agricultural and food business, you would see the pesticides make use of isotopes to help kill insects. We also use isotopes to generate gamma rays, which is going to irradiate the food before it goes to the store. And what this does is it kills bacteria that are present on the food, allowing a longer shelf life for produce, canned goods, and meats. Many of the tests that you would go to the doctor for rely on isotopes. MRIs, X-rays, CAT scans all make use of the isotopes that are found in your body. They may add an additional dye, which are going to add additional isotopes to help detect certain things. Blood tests may also add isotopes to your bloodstream to detect certain abnormalities also. In research, we often use isotopes for tagging certain things and trying to date how old something is. Two of the most common forms of dating or determining age are carbon dating and using oxygen isotopes to determine what conditions were like in previous centuries or even millenniums. So carbon dating makes use of, there's a certain amount of carbon-14 that's found in your body and in bones, and this decays over time to carbon-12. So based on the amount of carbon-14 that's left over, scientists can determine how old something is. Oxygen dating works the same way. We also use isotopes to determine how old a meteorite might be that has come to Earth.
Five, 4, 3, 2, 1, fire.
The last main use of isotopes is that of nuclear power. And so in the previous video you saw the 1946 demonstration of the atomic bomb being blown up. And this is where we get into our discussion of the nuclear power plant from The Simpsons. So the splitting of atoms or nuclear fission relies on isotopes that are unstable of uranium to generate power. This can be used to generate electricity, or it can be used for destruction in the form of an atomic bomb. Now that we've discussed what isotopes are used for, what exactly is an isotope? Isotopes are two atoms of the same element. They have to have the same number of protons and electrons. The atomic number is what determines what element an atom is. So if you have different number of protons, you're not dealing with isotopes, you're dealing with two different elements. What is different between isotopes of an atom or an element is that they differ in the number of neutrons and the atomic mass. Now that we know how isotopes are the same and different, let's go ahead and look at it using shorthand notation. So if I start out by using oxygen 16, which has 8 protons, 8 neutrons, 8 electrons, and we could write it out like this at the bottom here. And what that dash 16 there tells you is the atomic mass. You could look in the periodic table to find the atomic number then. Let's compare this to oxygen 18, which has the same number of 8 protons, 8 electrons, but now neutrons it has 10. And we could go ahead and write that out as oxygen 18 to show that it has a different atomic mass.